Okay, welcome back to the C++ course. This is Chapter 8. We're going to be talking about arrays and vectors today. And first of all, disclaimer, if I sound particularly nasally, public school has been back in session, and with that comes sickness and disease for the whole household, aka I'm getting over a cold. So just bear with it if my voice seems a little more crackly than normal, but we'll get through it best we can. So yes, Chapter 8, Arrays and Vectors. Some good topics here. And probably some things that maybe you wish you could have been using in other lessons or assignments, but maybe didn't know how to do. We're going to dive right on into it here. So we're going to talk about arrays, what they are, and how they actually can hold multiple values. We'll look at how to access individual array elements, how to input and display array contents, so how to print out the contents of an array. There are various ways to actually fill an array up with data. We're going to look at a very specialized form of looping called the range-based for loop. Relatively new feature added to the C++ language. Many other languages have this feature as well. We're going to look at how to process array contents, use parallel arrays, take a look at the typedef statement. This does not pertain to arrays necessarily, but it's kind of one of those one-off random topics that they threw in this chapter. We're going to see how we can pass arrays to functions as arguments, take a look at 2D arrays, and I suppose even higher dimensions than that, so arrays with 3 or more dimensions. We'll take a look at something called the STL, which we haven't actually looked at yet, and accessing the vector out of the STL. And just so you know, the STL stands for Standard Template Library. It is very much a C++ specific library, but the concepts and things you get inside of it can be applied to virtually any language. Then we'll take a look at how to store arrays of objects. So I'm going to do my best this chapter. I know these lectures get long. They get long for me too. This presentation is like 100 slides long. So we'll try to do our best to expedite things a little bit this week. So arrays in general hold multiple values. They're sort of like lists of variables. You can think of it kind of like that. It's a variable that can store multiple values of the same type. So right now where we are in the class, we can assume that arrays must hold data of the same type. So an array of integers, an array of doubles, an array of strings or chars. And these values are stored in consecutive memory locations, meaning in our computer's memory, if we have a 5-element array or 5-element list, all 5 elements are going to be next to each other in your computer's RAM. That is important because of speed. So if all of the memory in our array is in virtually the same area of memory, that means we're going to be able to access it and change it very quickly. So arrays and vectors are not the only two ways to store like lists of things in C++. There are many different ways to do it. Each have advantages and disadvantages, but you can count speed as one of the advantages of using an array. One of the disadvantages, by the way, is that they're fairly inflexible, meaning you can't really grow or shrink an array once you've kind of created it, but more on that later. Declared using square bracket syntax. So if we declare a const int called iSize and assign it equal to the integer 5, we can create an array of 5 integers like this. So we say that the array is going to store a bunch of ints. It's called tests, and then open square bracket, close square bracket, and in those brackets is where we put the size of the array. So this is where we say we're going to store 5 elements inside of this int array called tests. Here's kind of the standard visual of what an array, kind of how to think of an array in your computer's memory. And so the same array here, and basically you can think of it as like a list of squares kind of laid out next to each other, since they are, by the way, next to each other in your computer's memory. We have 5 cells here. So element 0, it's important to note that we start with element 0 or index 0 all the way up to element 4. So the size of this array is actually 5. There are 5 slots if you count them, but the only way to refer to them is by element 0 through element 4. There is no element 5 in this array. If you tried to access element 5, you'd either get an array out of bounds exception, or you would access basically just like random junk data in your computer's memory. But again, more on that later. Think of an array using this mental picture, basically. Array terminology. So in this definition, int is the data type, tests is the name, iSize in the square brackets is the size declarator. Another new term for me. I just call it the size of the array. Shows the number of elements in the array, and the size of the array is the number of bytes allocated for it. So check it out. You could say that the size is going to be equal to the number of elements, so in our case 5, times the number of bytes needed for each element, which whatever that is for an integer. So if you need 4 bytes for an int, that would be like 5 times 4 bytes. 20 bytes would be the size of the array. Don't quote me on the size of the int, though. Another example. So assume the int uses 4 bytes. Hey, I was right. And double uses 8. So here we have two constants, iSize and dsize, 5 and 10. So int tests iSize, which is 5, holds 5 ints. The array occupies 20 bytes in memory. Here are volumes is of size dsize, which is 10. So we have 10 doubles, which basically holds 80 bytes of data. How do we get at individual array elements? So each element has a subscript used to access it. And subscripts, as I mentioned, start at 0. We're going to be hammering on that basically throughout the entire chapter here. We want to make sure that when we're talking about arrays, we start counting at index 0. Again, it's a 5-element array. If we start at 0, that means our last element is index 4. There is no index 5 element here. So the formula for this, and when we start looping through arrays, this will become important to remember. The formula for this is the last index equals the size of the array, in our case 5, minus 1. That will give you the size of this array. Okay, so how do we actually get at array elements? Array elements are accessed by the array name and the subscript, and we use the square bracket notation to do that. And it can be used as regular variables. So you can treat them, you can use them just like regular variables as far as cin, cout, doing math on them, etc. So here we have a tests array. We're going to say open square bracket, close square bracket, index 0, so the first element equals the integer 79. So we can print that out to the screen. We can cin into it. And then we can do things like this. We could say tests at index 4 equals tests at index 0 plus tests at index 1. So that's going to assign this 4th cell equal to whatever's in the 0th cell plus whatever's in the 1st cell. And if we cout tests, illegal. So that's invalid due to missing subscripts. So we can't just print out the array. We have to either use like a loop to loop through all the elements in the array and print them out one by one, or we just print out the individual elements themselves, like tests at 0, tests at 1, etc. So how can we input and display array content? So as I said, you can use cout and cin to display values from and store values into an array. Another example with a 5-element array, you can print out, enter the first test score, cin, tests at 0. So I want to back up here and just kind of point out like how handy this is just from a practical standpoint and programming. If you had, I don't know, like 100 test scores you're trying to store in your code, instead of creating 100 different variables, test 1, test 2, test 3, test 4, you could just create a 100-element long array and fill them up that way. You don't need to declare and initialize 100 different variables. It's one of the big benefits of using arrays. And the other benefit is that we can fairly easily loop through them. So we can loop through and access all the data in this 100 or 1,000 or 1 million element long array pretty darn easily. We can access it and fill it up pretty quickly and easily using our handy looping structures, most commonly a for loop. Let's check out a hands-on here. And I'm going to, just for the sake of keeping hopefully this a little bit shorter, Definitely not going to hit all of the hands-ons. We'll take a look at them and read through them, but as far as typing them out all from scratch, I think the days of doing that are somewhat numbered, except for the bigger, more relevant examples. But yeah, let's create a new project. Console app, chapter 8 is the solution name. Let's see, EX 8.1, chapter 8. Create. Let's hop over to the textbook here, page 517. There's all kinds of cool graphics and illustrations of arrays if you need some more examples on why and how they are useful. All right. Apologies for the jump cut there. So one of the cool things about arrays is that they are native to the language. They're pretty much baked into C++, the language, so we don't need to do any custom including or anything like that. They're just a feature of the language itself. So let's create a const int num employees, and there's a reason why we use const here. Int hours num employees. All right, so we're gonna see out enter hours worked by num employees. Okay, so we can see in, just like we would expect, hours at index 0, see in hours at index 1, see in hours at index 2, then I'll comment, etc. That's one of my favorite things to do, etc. And then we can just see out hours entered are, let's see, see out hours at index 0. And sure, that's all we'll print out there. 6 employees. Okay, 1, 2, 3. Hours entered are 1, so that's the first one we entered. I am curious, just because I like to play and break things. Let's see what happens if we see out. Let's do this. Let's see what happens if we print out hours at location, I don't know, 99. One, two, three. All right, so it's just 0. We didn't even get an exception. Oh, that's interesting. So Visual Studio is smart enough to know that that's sort of out of bounds for that statically defined array length, but we didn't get any visual warning from the actual running program, so that's kind of interesting. Okay, that's basic array syntax. So array subscripts can be an integer, constant, integer variable, or an integer expression. So we can see into the test array like this, or see inning to index 3. The subscript is an integer constant. We can see out using an int variable, or we can even put math in the subscript, so we can add 2 numbers together to get at a particular index. You can do all kinds of math in there. It just has to be an expression that evaluates to some integer. The common denominator, all this, is that all of these are integers. Our subscripts are integers. There's no like array element 2.5 or array element 4.9. They must be whole number integers. Accessing all array elements. So that hands-on was pretty tedious because we had 6 employees and we were C-inning and C-out one by one. A loop makes this much faster. And the for loop definitely is the way most people go to do this. So we start with our for syntax. For I equals 0, I is less than 5, I plus plus. So I is less than 5 means that we're assuming valid indexes are from 0 to 4. So this is a 5-element array. And we just see out tests at index I. So that's why on the previous slide we mentioned that you can use I when you're subscripting your array syntax. You just print out whatever I is, tests at location I, followed by a new line. Let's do this hands-on. 82. This is fundamental enough syntax where I feel like it'd be good to actually type through this by hand, though, of course, if there are exercises in the textbook that I just go and talk about, but you guys want to actually go through and type them out by hand, definitely would not hurt. I would encourage such behavior. So include IOStream, namespace standard, const int num imps equals 6, int hours is our array. The size of this array is num imps. We have a counter variable, int count 4. Do it like this. Count equals 0. Count is less than the size of the array, num imps count plus plus. So we certainly didn't have to declare count outside of the for loop. We could just use like int I equals 0, whatever. Cout, enter the hours worked by employee. Yeah, that's fine. Cout employee count plus 1. So it makes sense here that we're adding 1 to count. Notice that we're not permanently, we're not reassigning the value of count. We're just displaying, we're printing out the value of count plus 1. There is no equal sign here, so we're not actually modifying the count variable itself. We're just printing out what count is plus 1. There's no assignment there. And it makes sense because if you're a user working with an array, you want to see employee 1 if you're entering data for your first employee. Users typically don't like to see employee 0. So we're just kind of faking, I guess, the prompts so that the user sees something that they'd be more comfortable with. Programmers like starting counting at 0. General users don't really. So then we can cin to hours at location count. And we can display. So in that for loop, we're cinning to our hours array. We can also print the hours entered for, I'll just do it this way, int I equals 0. I is less than num imps I plus plus. Just as a refresher, I'll omit the curly braces here. So cout, I hate the variable name count because I always get it confused with cout. Cout space followed by hours array at location I. Right? HOURS. Why you know like this? Is less than, okay. For int I equals 0, I is less than number of employees. Were you expecting a semicolon? Oh. There. Beautiful. All right, cout end line, or just return 0. Activate the project. All right, enter, okay, 1, 2, 3, 4, 5, 6, keep things easy. So that was a loop to handle the inputs and a loop to handle the outputs. Easy peasy. Getting array data from a file. You can also read data from a file sort of into an array. So here's some syntax for doing that. So we still declare a const int of our array size. We create our sales array of size I size, in this case is 5. We've got an input file stream handle called data file. We open the file. This is nothing new. We've worked with external files in other chapters. We open up a file called sales.dat if we're not able to open it, basically display an error and return. Otherwise, we're going to input daily sales. So for int day equals 0, day is less than size, which is 5, day plus plus. And then we're going to input into our sales array at location day from our data file one by one in our for loop, and then close it up. This will be one that we'll just take a peek at here in the textbook. Seems like kind of a random one-off example, like, okay, cool, I can read data from a file into an array, but basically here's the file name, work.dat. Remember, the file name on these things doesn't so much matter. It's the contents that we really care about. As programmers, we could have called the file work.xyz or ABC. That does not matter. The file extensions are really only important for like your operating system like Windows to know what to do with the file. Really, all we care about is that the file contains what's called plain text or ASCII data. It's not like Microsoft Word data or binary data or hexadecimal data. It's really just ASCII data or plain text. Basically the same kind of data you'd find in a text file, TXT file. All right, but the contents of this listing is basically the same as what we saw in the slide. So we're looping through, read the numbers from the file into the array. When we exit the loop, the count will hold the number of items that were read in. And this is somewhat, I would say, inflexible, because we kind of have to know at compile time how many employees are in that file. We have to know that there's exactly 6 employees in that file. That's what makes this fairly inflexible. There are ways around this that I'm not sure we may get into with the vector stuff at the end, but with plain old C++ arrays, there's not a good way to go around this, other than like copying the contents of one array into another array of size +1. You could do it that way, or size -1 if you want to shrink the array, but that's pretty darn cumbersome. There are much better ways. Similarly, you can send data to a file. You can open the file using an OF stream and use a loop to write each array element to the file, then close it up. I don't think there's a hands-on for that. No. Okay, so this slide here goes back to what I was saying earlier about bounds checking. And the idea that our arrays are of fixed size. There are no checks in C++ that an array subscript is in range, though as we saw, Visual Studio kind of hints or nudges us that, hey, this is looking pretty suspect. You might want to check your index and make sure it's within the size of the array bounds. An invalid array subscript can cause the program to overwrite other memory. If that sounds dangerous, you'd be right. It's not as dangerous as you might think. Like, the operating system itself won't let us write data into very, very critical pieces of, for example, Microsoft Windows. There are security measures built into the operating system that prevent us from doing that. But it's still, we still are writing data to random locations in memory that we really shouldn't be. So an invalid array subscript can cause a program to overwrite other memory like this. So if we have an array of size 3 and we have an integer I equal to 4, we create a num array of size 3, and then we try to access index 4 of the num array and assign it some value, 25. Well, C++ is going to let us do that, and we don't know what piece of memory we've just overwritten on our computers. It is probably nothing. It probably won't hurt anything, but we don't know that for sure. Let's check out this hands-on. Program unsafely stores values beyond an array's boundary. What happens depends on how your computer manages memory. Hopefully, it manages its memory well. It may overwrite other memory variables and may crash your computer. May. So all those mays should throw red flags in your mind. And the fact that we don't know what's going to happen, that's dangerous. Similarly, I should show you guys something like this. Let's do like a for int j equals 99. J is less than Oh, no. J equals 0. J is, I know how to write a for loop. J is less than 100. J plus plus. Let's do something like this. C out. Let's do it. Hours at location J. So we talked about writing to invalid array indexes, but what about reading from them? Is that dangerous? Well, not really. Read only is typically not a dangerous thing to do, but it's not going to make much sense. Let's take a look. There. Random junk data scattered throughout our computer's memory. We don't know what this is or what it means. The computer probably does. The computer's managing this, but we don't know. Man, I'm surprised it even looks that nicely. Sometimes we'll get all sorts of strange looking ASCII characters, like ASCII characters you didn't even know existed, smiley faces, weird texture looking tiles, things that go way beyond the keys you see on your keyboard. All right, and that's what this example 8.4 kind of demonstrates. All right, off by 1 errors. This is one of the most common errors in all of computer programming. These most often occur when a program accesses data in one position beyond the end of an array, or misses the first or last element. This is definitely because we start counting array indexes again at 0. And the last valid array index is the size of the array minus 1, which is exactly what this second bullet point says. So other ways to initialize an array. So we saw one way, or basically we say, here's an array of size 10, and then all of the elements in that 10 element array are either junk data or they just contain nothing. So it can be initialized during program execution with assignment statements like this, which we've seen, or you can sort of do it all at once with some syntax like this. So if you have an array called tests of size 5, you can fill that array with 5 pieces of data right away with the opening and closing curly braces. This is called an initialization list. Hands-on 525. Okay, finally some different data types here to be used with our arrays. So it displays the number of days in each month, uses an array of string objects to hold the month names, and an int array to hold the number of days in each month, both initialized with initialization lists at the time they're created. So we do have to include the string library, and this is actually, to be honest, peeking ahead a little bit in the chapter. This is what's called parallel arrays. So these two arrays exist separately in computer memory, but they kind of track similar data. So one array contains 12 names of the months of the year, and the second array, both of size 12, contains the number of days in each month. Again, using that initialization list. So this just shows that you can create an array of strings with all the month names, and this just shows what we're used to, basically an int array. And then when we loop over it, we can set some text formatting, but we can print out, for example, the name array at index month, which starts at 0 here. Then we can print out the days array at index month. So they should match up. That should keep the output of both of those arrays basically in sync because you're using the same index to print them. So start element at 1 or 0. You may choose to declare arrays to be 1 larger than needed. That's tempting because then you can just say, hey, my array starts counting at the number 1, or basically the first element, and minimizes off by 1 errors. But the element with subscript of 0 is not used, so that basically is wasted memory, and it's just not done. Like, we need to remember that we count arrays starting at 0. Often done with working with ordered data that logically begins with 1, like months of the year or days of the week. I still wouldn't do that, however. Okay, parallel arrays, as my voice slowly fails here. If an array is initialized at definition with fewer values than the size, the remaining elements will be set to 0 or the empty string. So when we were working with the initialization list of creating an array, you might wonder what happens if I don't specify enough values to fill the array. Well, basically going to be filled with 0. So the initial values are used in order. You can't skip over them to initialize a non-contiguous range. You cannot have more values in the list than the declared size of the array. Yes, I even marked this one as read only because it's so small. So the program has a partially initialized array. So we've said the array is size 7, but we're only basically filling in the first 4 elements here and then printing out the whole thing to prove that the rest of them will be filled with zeros. Okay, so earlier we've been talking about arrays. When we declare them, we've always put like a size in the square brackets. How big is the thing going to be? But if you don't want to do that, you can have it sized implicitly when you create an array using an initialization list. So we excluded the size here, but we fed it basically 4 elements. So the compiler will know that this is a 4-element array, even though I didn't specify that here in the square brackets. Must use either an array size declarator or an initialization list when the array is defined. You have to do one or the other. You have to feed it a size or feed it an initialization list. It has to know at compile time what size the array is going to be. Here's some other ways to initialize variables, including arrays. You can initialize a variable at definition time, so something like this, which is kind of interesting. So we're used to int length equals 12, but you could say int length, open close paren, 12. Okay, cool. In C++ 11 and higher, you can also do this. So put it in curly braces. Second approach checks the argument to ensure that it matches the data type of the variable and generate a compiler error, or if not. So it's a little bit safer, I suppose. It will kick out an error if it's type mismatched. Cool, so the range-based for loop. We've seen the while loop, the do while loop, and the for loop. Here is a slight modification on the for loop. And lots of different languages have this kind of syntax for their for loops. And it's more or less just a convenience for us as developers. A lot of times when we're iterating or looping over an array, we don't necessarily care about the index. We do care about the index only because it's giving us access to each element in the array. But with the range-based for loop, we're getting that element without having to specify an index. And it looks like this. So for data type var, colon, array, and then a bunch of statements. So data type is the type of the variable or the type of thing that's in the array. Var is a variable. And then statement is a loop body. And how I read this, and I think it makes it somewhat human readable, better than this format. Basically for data type var in the array. So for each, and other languages call this a for each loop, by the way. So for some data type I in the array statements. We just talked about that. Let's take a look. Yeah, here we go. So sum the elements of an array. So if we have an array called grades, sized via the declaration list, or the initialization list, and we have some integer called sum equal to 0. Here's our range-based for loop. For int score in grades. That means as we're looping through the grades array, each individual element in that array will be stored in the score variable. So when we loop through grades, the first time we loop through it, score will have the value of 68. We'll keep the running sum going. The second time, score will keep the value of 84. The third time, score will have a value of 75. So again, there's no I, there's no like count, no plus plus, anything like that. This, like I said, is more or less a convenience method for us to quickly loop through arrays and lists. Here's another example. We can also modify the contents of the array. So here we have const int size is 3. Create an array of size 3 called grades for int reference score inside of the grades array. You can see into it. So we're getting a reference to it, not a value, copy of it, a reference to it. All right, 532. Just a little listing here. I won't actually go and type it out. So here we have a planets array or a string array. Display the values in the array. Here are the planets, and we can loop through it. So this reads for string val in planets, or for each value in planets, print out the value. So the first time it'll print out Mercury, then Venus, then Earth, etc., with some hate being thrown on Pluto. I guess we still don't know what that is. So again, just a convenience way to quickly loop through arrays and lists. So a comparison between the two, comparing a for loop versus a range-based for loop. So the range-based provides a simple notation to use to process all the elements of an array. Notice it says all. So there's, at least we haven't seen yet, a way to only process a portion of the array with the range-based for loop, or I may even call it a for each loop here moving forward, because that's what I'm used to working with in C#. So range-based for or for each, we'll kind of treat them as the same thing. However, it does not give you access to the subscript. So like I said, there's no I here or no count here. That may not be a good thing. If you need to have access to that index or that subscript, the for each loop or the range-based for loop may not be for you. If you need to know the element locations as well, then use a regular for loop. So definitely certain times when you should use a for or a for each. So pretty straightforward there. Let's see. Okay. So modifying the array with a range-based for. And again, they are using a reference instead of a copy here because they want to modify the original value of that element in the array. And then we can display them by just using the regular for each loop. So for val in numbers. For each. I actually like the each in there because it's a little more expressive in what it's doing. For each integer val in the numbers array, do whatever you need to do with val. Processing array contents. So array elements can be treated as ordinary variables of the same type as the array and can be used in arithmetic operations, relational expressions, etc. So anything you can do with a regular, in this case, int variable, you can do with an individual element of the principal amount array. So you can compare it, you can do math on it, you can assign it to other things. Pretty common sense stuff there, if I can say so. So next, hands-on. I hope this format is working for you guys, maybe better than hand typing out each example. If you have any feedback on it, feel free to let me know. If you don't care that I'm kind of going a little faster here, if you'd like me to keep going at the snail's pace that we were doing, I'm definitely open to feedback. So hit me up with that either in the discussion sections or just via a quick email. Okay, uses an array to store the hours worked by a set of employees who all make the same hourly wage. So here is where we're going to, I guess, work with processing the array contents. We have a num workers constant and using it for the size of our hours array, which is 5. We've got a double pay rate and a double gross pay. So we're going to use the regular old for loop to see into the hours array. And remember the worker plus 1 here, that's again just so the user can see that I'm dealing with employee 1 and not employee 0. And remember, that does not actually modify the value of the worker variable. It's just basically increasing it by 1 for display purposes. Then we're inputting the hourly pay rate for all employees. And there's some prompt here, and we're inputting the pay rate. So we've already got the number of hours worked for each employee. Then we're going to grab the pay rate from the user. Then we're going to display the employee's gross pay. So here we're going to loop through the hours array. We're going to access the number of hours worked for each element in the array and multiply it by pay rate. and then we're just going to display what that is. Again, increasing the index we're using to access the array elements by 1 for output purposes. All it's doing is showing that we grabbed the array contents from the user, we grabbed the pay rate from the user, and we're just doing math on each element of the array, displaying what that gross pay is. That was 810, yes. Using increment and decrement operators. So when you're using plus plus and minus minus, and this is fairly nuanced, don't confuse the element with subscript here, okay? If you put the plus plus outside of the closing square bracket, it'll add 1 to whatever tests at location I is. So this is like saying num plus plus. You're taking whatever is inside of num and adding 1 to it. Here, though, you're taking the index and adding 1 to it, but has no effect on the actual contents of the elements themselves. Copying one array to another. Okay, so how do we do that? You can't copy with an assignment statement. So if we have two arrays of the same size, tests2 and tests, you can't just test2 equals tests. Even though they're the same size and the same data type, that will not work. And there are specific reasons why this does not work. Under the hood, when we're working with arrays, we're actually working with something called C++ pointers, which is a critical thing to understand in C++, but is definitely an advanced topic that we'll circle back around to in a later chapter. We're going to talk about arrays again when we start talking about pointers, because hint, hint, you're already using pointers when you're using arrays. You just don't know it yet. But for very particular reasons, this will not work. Instead, if you want to copy an array, use the loop to copy element by element. So if we do have two arrays, test2 and tests, we simply loop through it. So starting their index at 0, keeping it less than size, index plus plus. We're taking the contents of test2 at location index, assigning equal to tests at location index. Hopefully no surprises there. Our two arrays equal, so like copying, you can't compare two arrays like this. Wouldn't that be nice? You can, though, use a while loop and a bool variable to check and see if they're equal. So we start out creating a bool called r=, and assigning it equal to true. And we have our array index here. And this is just, I assume they're just showing us that we don't have to use a for loop. When we're looping through an array, you can use a while loop to do this. So while r= is true, remember this is just shorthand for r= equals true. So while r= and index is less than size, do stuff. If tests at location index is not equal to test2 at location index, set it to false, increase our index, and loop around again. So if they are not equal, this now becomes false. And when we jump back up here to the condition of the while loop, this becomes false and the whole condition fails because we're using an AND. Remember, both conditions must be true when we're working with an AND condition. And when that becomes false, this whole thing fails and we move on. So this is actually quite an efficient way to do this, to check and see if two arrays are equal. Because say you have a million element array, you want to compare it to another million element array. Well, if element 1 of, should say element 0 of both of those arrays is not equal, we're going to check element 0. If they're not equal, we'll set this to false. And when we go back up here to the condition, we'll just quit. There's no sense in checking the rest of the elements of the array to see if they're equal, because we know that the first one is not. So don't waste your time checking all the rest of the 999,000. Just break out of it and keep going. So we can find the sum and average of array elements. So we can use loop to add together array elements, float average, and sum equal to 0. We keep a running sum like this. I've actually seen this in a previous example. Or you can use the C++11 range-based for like this. And once you've summed them, you can calculate your average just like we've always done before. Here, our I size contains the size of the array. So that's basically what we can take sum divided by to get our average. Here's a little algorithm to find the largest array element, so we can use a loop to examine each element and then find the largest, or the one with the largest value. So when we start this little algorithm, we can say int called largest equals tests at location 0. So we're basically going to assume that the largest element of the array is the first element of the array because we have nothing else to compare it to yet. So then we're going to enter our for loop, say int tnum equals 1. Tnum is less than isize, tnum plus plus. Why are we starting at 1 there? Why is tnum set to 1? Because we've already dealt with the 0 element of the array. Now we're going to compare. If tests at tnum is greater than largest, now largest becomes tests at tnum. And we go through this over and over again until the array is done, basically comparing each element of the array, seeing if it's greater than whatever our current largest is, and then printing it out. You can do the same thing with finding the smallest element. You just flip this to less than, and you're good to go. The question, of course, is what happens if the elements are equal? Well, because they're equal, it wouldn't matter. We would not be doing the swapping if they're equal here. We're strictly greater than or less than if you're doing the smallest number. But you could slap an equal sign on there and it would do the same thing. So why would we want to use arrays versus simple variables? Well, if your input data is only processed once, you, I guess, don't really need one. Like if you're finding the sum or average of a set of numbers, finding the largest or smallest. If the input data must be processed more than once, an array is a good idea. Calculating the average, then displaying which are above, which are below, etc. Let's check out a hands-on. So, uses an array to store monthly sales figures for a company's regional offices, finds and displays the total, average, highest, and lowest, and then the data to fill the array is read in from a file. So nothing super new here, more of just like a combination of things we've seen so far. So we've got an input file stream handle called data in. We've got num offices constant, size is 12, an int called the office, and then we've got a sales array, which is a double of size 12, double total sales, average sales, etc. So we're going to open up the data file. We are going to fill the array with data from the file, which we're going to assume is 12. It doesn't have to, it could be more than 12. So the data file could have more than 12 pieces of data in it. But if it does, we're basically going to ignore them. That's what, again, makes this fairly inflexible. But we are going to read in every line into our array. And that makes it really easy to then go through and process or number crunch things in the array. So we can do things like keep a running total of the sales. So for our index is office, sales at location office. Just increment that onto total sales. Can calculate the average. Then using the algorithm that we looked at in the slides, we can find the highest and lowest. And then we can just display that information at the end. That's nice, because instead of, let me go back a slide. Instead of having to have 12 12 sales variables like sales 1, sales 2, sales 3, all the way up to sales 12, instead of having all those separate variables, which it could do, we're just creating a single array that is of length 12. Saves us some typing, saves us some headaches, especially when the amount of data that we have to crunch gets larger and larger. Okay, the exact amount of data and therefore the array size may not be known when a program is written. So this goes back to what I was kind of talking about earlier, where we need to know what this size is, kinda. The programmer makes a best estimate for the maximum amount of data, then sizes the array accordingly, and a sentinel could be used to indicate end of data. The programmer then has to keep track of how many elements are actually used. What does it mean by a sentinel? So that would be like if we created an array of size 100, and then we're filling the array up, we're putting things into it one by one, and say we get to array element 50, and we know that's going to be the end of it so far. So the sentinel, we could put like, I don't know, a -1 at array element 51. And then if we're doing something like looping through the array, we would know to stop processing the array when you hit -1. Then if I decide to put more data into that array, say fill it up to 75, then I would put my sentinel at location 76. Then when I'm looping through the array, the loop, we could tell it to stop processing the array when it gets to that -1 at location 76. And so that would be just a little bit more optimization, time-saving kind of thing. Not particularly useful for smaller arrays like 100, but for 1,000 or million element arrays, definitely would have some impact. All right, C strings and string objects. So here's something kind of cool. We've been using arrays when we've been working with string objects, but we haven't maybe realized it. Can be processed using the string name, either the string at once or one element at a time. So you can process the whole thing at once, or you can loop through it one element at a time by using a subscript. Here's what that means. If you have a string called city, and you're entering a city name, you grab it from the user, this is actually creating an array of chars. Okay, we didn't know that. Behind the scenes, when we started talking about strings, we were creating an array of chars. Single character elements. So city at element 0 contains the character S. City at location 1 contains A, on down the line. So city name is Salem here. Okay, and we can process that. We can loop through that just like we loop through any array. Only now we're printing out chars instead of ints or doubles or things like that. So that's how strings are treated behind the scenes. This is actually called a C string. This is how the C programming language does this. Okay, 544. Here's another example of that. So here you have a string W-A-R-R-E-N or Warren, or behind the scenes, if that's stored in a name string, you can access each character, each letter individually using the subscript notation. And I think that's what 813 is going to get at here. So we've got a string called letters assigned to ABC lowercase, ABC uppercase. We've got a char variable called the letter. You can probably see where this is going. Print the table heading. Oh yeah, print the table heading, so letter code. We've got a numchars integer assigned equal to the length method of the letters array. So the letters array, which we know is a string, but we're talking about arrays, so I refer to it as a string or a char array. Give me the length or how many letters are in that array, assign it equal to numchars, and that is what we're going to use in our for loop. So while POS equals 0 and POS is less than numchars, add 1 to POS. And again, here we're just kind of looping through each letter, printing it out. We do have the static cast here, and that's kind of the point of the code. So what they're doing, we're grabbing each letter one by one from that string, and then we're taking that character and statically casting it to an int. So all it's doing is showing us what the ASCII representation of that character is behind the scenes. And here you can see a sample output. So A is 97, B is 98, etc. Uppercase A is the classic 65. Alrighty, 545. I think we'll gloss over that one. You guys can check that one out if you would like on your own. Parallel arrays, so 2 or more arrays that contain related data. We already saw that with the titles of the months on the calendar, and then a separate array that's sort of set in parallel that keeps track of the number of days in each calendar month. You could do it like this. If we didn't know about things like structs, if we didn't know about things like classes and object-oriented programming, this would be a good way to handle like groups of related data. So what we've done here is created a string array called name, a float array called average, and a char array called grade. All of them are size 5, and all of them, we will assume, are related. So name at location 0 average at location 0, and grade at location 0 all represents basically like one student. Element 3 contains the name of the, fourth student, the average grade, and the letter grade. And that's cool. It's pretty simple and straightforward to see how that would work. The caution, though, with that, of course, is you have to be sure that you're not getting out of sync. All three of those arrays have to be kept in sync so that Bill's name here really reflects Bill's average and Bill's letter grade. That Bill's not getting Susie's average or Susie's letter grade. You've got to keep them in sync. And when you process them, you can process them like this. It's kind of tricky to get them out of sync actually, just because of how we usually process them with our for loop. But if you've got those three parallel arrays and you're looping through it, you could just say, give me student at name at index I, average at location I, and then grade at location I2. 547. Generally, I would say parallel arrays aren't a good idea. Usually using something like a struct or a class would be better than using parallel arrays, just because of the synchronization issue. And it's just, I haven't really seen them in the wild that much. People prefer to use a more robust data structure than a parallel array. Here's an example illustrating that. So we've got two arrays here, hours and pay rate. Those are our parallel arrays, both of size 5. We're getting the employee's work data, and we're going to do that by looping through it in a for loop so we can see into the hours array at location index and pay rate at location index. That's what is keeping the parallel arrays in sync. Once we've got that information, we can print it out, again, doing the same notation, printing out the hours array at location index and multiplying it actually by pay rate at location index. So we're not directly printing out what those contain, we're printing out a multiplication of the two. Perfectly fine to do that. Grab a drink of water here. Okay, shifting gears a little bit to something called the type def. So the keyword type def is a C++ keyword. Type definition is what it's short for, if you couldn't guess. Basically, this creates an alias for a simple or structured data type. And we have the format here, the syntax. We say type def followed by existing type or existing types. I would say type, something like this, because it could be one or more, and then the new type name. So this is really a way of aliasing a complex data type down to something that's a little shorter. So here's an example, type def. Then we have, that's the keyword obviously, existing types, unsigned int. The new name then is uint. Okay, so here, instead of having to say unsigned int every time we want to create an unsigned int, we can just say uint instead. And we can do that with our arrays. We could create a uint array called tests of size I size. And instead of having to say unsigned int tests I size, we just say uint. For those of you in the game development courses, Game Dev 2 in particular, we see the type def used a lot in the Unreal Engine course. Fair warning on that. It can be used to make code more readable. Again, it cuts down on syntax because instead of having to specify a long, complex data type that's chained together, we can just say what the alias is. So here we have a year array as a data type that is an array of 12 ints. So we could say type def int year array months. I actually didn't know you could do that, but you can. So it can create two arrays, two of these arrays. And it looks a little strange because this is actually our data type now. That's our new type name. So we can declare it like this. Year array, high temps, low temps. So these are two arrays of type year array, which is an array of ints. So you have to kind of trace it back to the origin of where that type def statement comes in. But as soon as you do that, you can see exactly what year array, what that type is. Okay, how do we use arrays as function arguments? So we can pass a single array element to a function. That's no different than passing a regular variable of that type. So the function doesn't need to know that the value it receives is coming from an array. It doesn't care at all. So if we have a function here called display value that accepts an int called item, we can see out item. And as the slide mentioned, we don't care that this int item came from an array. When we call display value, we can pass in an integer, just a regular old int variable. We can pass in a constant integer, or we can pass in an integer inside of an array element. So we say score at location I. Or you could pass an entire array like this. So you could define a function that has an array parameter, use empty, open, closing square brackets to indicate the array in the prototype and the header. So this is what that looks like. So to tell show scores that it needs to accept an array of ints, you say the data type space open, closing square brackets. The function header would look like this. So remember, prototype is what we see up above in main that gives the program sort of a preview of what this function is going to look like, what its return type is going to be, and what its inputs are going to be. Then the function header, again, returns void, but it accepts an array of ints, and now we specify the parameter name. When you call it, you just pass in your tests array, and it's good to go. So when you're passing an array, use the array name without brackets as the argument. So that's actually worth going back here. When we called the show scores function, we passed in a tests array, but there's no square brackets here. We're just passing in the name of the array without the brackets. You can also pass the array size as a separate parameter, so the function knows how many elements to process. That's just sort of a convenience thing. You could pretty easily write some code to get the size of the array, but if you know when you're calling the function how big that array is going to be, you can go ahead and specify that just as, like I say, a convenience to the function definition. So here we have a show scores function that accepts an int array and an int, which is the size of the array. This would be the prototype. So in the header, we actually have to give those things names. So A is a capital A is typically what's used for an input that's of type array. So we have an array of ints, and we have an integer called size. When we actually call the function, we pass in the name of the array and how big it is, in this case 5. Let's actually do this hands-on on page 551. $8.16. Wow. All right. Making good time here. Not that there's any huge rush, but I know everybody's time is valuable, and try to just point out the high points here. Okay. Using the standard namespace, we have a function prototype void show value, which I'm going to write in upper camel case. Show value accepts an int. Let's define the function down here. Void show value accept an int called num. See out num. Well, this is boring. And then it's going to show us that we can call that. Doing something like this, const int array size equals 8. Int collection, name of our array is of size array size. And then we initialize it to some numbers. Sure. Now we can enter into a for loop for int I equals 0, I is less than array size, I plus plus. And we can call show value, passing in our collection array at location I. All right, 8.16, set as startup, run it. No surprises here. Again, this is just showing that we can pass array elements into functions. Okay, using typedef with a passed array. So you can simplify function prototypes and headers. In this case, if you typedef this, now you can say typedef int name of the typedef, and that's going to be an array of ints. You can say this, our custom typedef, and int. So we're using this name that we created up here as the type of our input to this function. A little confusing, but just trace it back to the original typedef, and you should be okay. All right, modifying arrays and functions. Array parameters and functions are similar to reference variables. Changes made to an array passed to a function are made to the actual array in the calling function. So that's actually a fairly important point. The programmer must be careful that an array is not inadvertently changed by a function. You could use the const keyword when you're passing arrays to your functions to prevent changes or prevent the original array from being modified. So that's it's worth mentioning again. Array parameters are similar to reference variables because if you pass an array to a function and modify the array in that function, the original array is changing. It's mutating. We don't have to specify an ampersand. That's just kind of how it works in C++. Changes made to the array passed to the function are made to the actual array in the calling function. Definitely worth committing that to memory. All right, so here's a little program that shows how to pass an array to a function. So here we have a show values array. Prototyped up here to show that we need to pass in an int array, an array of ints called int array, and an integer called size. And when we call the function, we simply pass in the array name, and in this case, we pass in the size of the array, and the function definition is down here. Notice, back when we called it, actually it's worth mentioning, we said collection, which is an array without any square brackets. So when we call it, we don't use the square brackets. When we define it down here, when we create the function header, we do specify the square brackets and the data type and the name of the parameter, of course, just like we always have, and then we can loop through it. Alrighty, 554. Demonstrates passing different arrays to a function. So we've got a typedef, which is going to be an int array called array type. Here's our function prototype called show values. It's going to accept our typedef, which is array type and an int. And remember, what is the type array type? Well, it's an array of ints. I wish they could be a little bit more creative in their typedef names because it could make this less ambiguous. That's what we have. So this is an integer array. Okay, so let's see what that function does. Down here, we can still use the typedef name, followed by our parameter name, and a keyword int, followed by parameter name size. So here we're just going to loop through and print out all the nums in our nums array. When we call this thing, here up in inside of main, we have two arrays, set1 and set2. Notice how they do have different sizes. That's actually important because when we call the show values function, we pass in set1, which is size 1, which is 8, set2, which is size 2, which is 5. So the function will know how many iterations it needs to make through that loop based on the size parameter that we pass in. Okay, here's kind of the good one that I really wanted to point out. So the program uses a function to double the value of each element of an array. Cool. So we've got that same typedef called array type. Array type is just going to be an array of integers. We've got a couple function prototypes here that use that type definition. Down here where the function is defined, we're using again our custom typedef name, followed by a parameter name called nums and an int parameter called size. Okay, that's fine. So we're looping through our nums array, but when we're looping through it, we're taking whatever is stored at the current index of nums and multiplying it by 2 and reassigning it. So this is demonstrating what I mentioned earlier. the original contents of the array will be modified when we pass it down to the double array function. When we call this thing, we just pass in this case, set. Where is set? Here. Array type set with a bunch of numbers in it. Specify the size. That's going to show those values. Then down here, we're going to double it with double array, and then we're going to show values again just to prove that the original values in the array were doubled. And checking out the output here, you can see that. 1, 2, 3, 4, 5, 6, 7, all the way up to 2, 4, 6, 8, 10, 12, 14. So the original values were modified. 8, was that 8? Yes, that was 819. 820. This, all I want to point out. Yeah, okay. A good function note here, or program note here at the top. Good comment. Passes an array filled with sales data to functions which find and return the total, highest, and lowest values. The function should not change the array, so they each use a const array pointer. So just a little keyword const here modifier, indicating that, let's jump to the function definitions. Inside of the functions, the array itself should not be modified. And that's as much a note to us as programmers as it is to the compiler that, hey, if the programmer is trying to modify the contents of array down here, throw a flag, throw a warning, because we've declared it const, meaning it should not be changing. And in fact, if you check the function, you will note that nowhere in the functions are we taking the contents of array and modifying them. We're grabbing them. We're getting them with array at location count plus equals total. Total plus equals array at location count. But we're never saying array at location count equals something. If we did that, we'd have problems because, again, we declared it const. Okay, two-dimensional arrays. So what we've seen so far is 1D arrays. You can define one array from multiple sets of data, and this more or less resembles a table in a spreadsheet. Uses two size declarations like this. So if we have a 2D array called exams that holds ints, the first dimension is 4, the second dimension is size 3. First bracket is rows, second bracket is columns. So 4 rows, 3 columns. And you could sort of visualize it like this. Okay, just as I said, you have 4 rows, 3 columns. And this is a nice graphic because it shows you what the indexes look like at each cell. So if you wanted to access the bottom right element, you would use exams at location 3, so row 3, or 0, 1, 2, 3. And the column is 2, or 0, 1, 2. Use 2 subscripts to access the element, either to read it or to write to it. Okay? So you can think of it as a spreadsheet, rows and columns, where the first square bracket is rows, second square bracket is columns. When you access an element of a two-dimensional array like this, the first subscript indicates the row, the second indicates the column. Though not always. You don't have to think of 2D arrays as rows and columns. It can represent much more than that, but turns out that most practical use cases, that's really what they're used for, rows and columns. If you think about video game development, particularly 2D game design, this would be like your, excuse me, this would be like your tile map, okay, where you have a grid of tiles being shown on a computer screen, or rows and columns of pixels. Okay, so your tile map would be a 2D array that's represented with rows and columns of tiles or pixels if you want to get really small. Initialization, this is a little confusing, but you can use an initialization list when defining 2D arrays. They're initialized row by row, so you still have the opening and closing curly braces for the entire array, but then each row of the array is inside of its own curly braces. So if you have a 2x2 array called exams 8478, 8478, comma, then you're in your next row. And a lot of times they do in the code format it like this, so you can visualize the rows and columns nature of your 2D arrays. The inner curlies in the initialization improve readability, but are not required. Would definitely recommend it though. The inner curlies can be used to initialize some, but not all elements. Let's take a look at a hands-on. Let's actually, it's got input from files. Well, we can just read through it. Okay, so we're creating a 2D array that's going to store the number of divisions and the number of quarters. So the number of divisions we have is 3. Number of quarters is obviously 4. We're declaring a sales array that has doubles in it of 3 rows and 4 columns. So the first square brackets is rows, second square bracket is columns, and some variable called double sales, or total sales of type double. We've got 2 ints, div, and quarter, and we're inputting from a file. I wish they wouldn't do that for examples like this. We've got enough to worry about without having to read from a file, but whatever, that's fine. We are printing out a header here, and we're going to use a nested for loop to fill the array. Okay, when you start talking about multiple dimensional arrays, like a 2D array, then in order to loop through that 2D array, you're going to have to start using nested for loops. And it looks like this. For div equals 0. Remember, div is basically our rows, so we're going to loop through each row one by one, but then within each row, we're going to loop through each column. Okay, so quarter starts with 0, quarter is less than num quarters, quarter plus plus. And then remember doing the +1 thing here just for user ease, make our users happy. We're going to read into the sales array at location div and quarter. We're going to fill that up with our input file. We could have easily done this with just manual input from the user, but it's using an input file. That's fine. The important thing to remember is that we're using a 2D array. The outer for loop is to loop through the rows. The inner for loop is to loop through the columns. Now you got to be careful when you're using nested loops, because if your 2D arrays start getting large, the execution time, the time it takes for this program to finish running, increases, I'll use the term exponentially. And that actually is a correct use of the term exponentially. We're going to talk more about that in a future chapter when we start talking about like runtime for programs. It's actually really interesting. It's when people say computer science, that's the science part of computer science, but that's coming. But here's a little preview. You can estimate how long or how many times this for loop is going to execute if you just multiply your rows by your columns. In this case, it's 12. It's no big deal. But if you had a large number of rows and a large number of columns, that could be a big deal because it multiplies and gets exponentially larger. You can, again, use nested loops to add all the elements together like so. But the important thing to remember with this, again, outer loop is for rows, inner loop is for columns, and you do need separate counter variables for them. You can't use div twice. I suppose you could if div and quarter were the same, but it would be significantly more confusing. You can pass a 2D array to a function very, very similarly to how you pass a 1D array. You use the array name and the number of columns as the argument. So get exams, you could pass in the exams 2D array, and 2 would be our number of columns. You could use empty square brackets for row and size declarator for the number of columns in the prototype and the header. Okay, so it looks something like this. Sure, you can use a type def to quickly declare 2D arrays. We already did this example, but you can use 2D arrays for traversal. Use nested loops, one for the row, one for the column, to visit each element. You can use accumulators to calculate the sum of the elements row by row, column by column. Here's the dirty little secret of programming. You can have arrays that have an arbitrary number of dimensions. So you could have an n-dimensional array. Typically, you don't have n-dimensional arrays. 2 or maybe 3 is the largest number of like nested arrays that I have ever seen, but there's nothing to keep us from having an n-dimensional array. Here's a rect solid 3-dimensional array. Here's a 4-dimensional array called time grid. That sounds pretty advanced. When the type of array is used as a parameter, specify the size of all but the first dimension. Cool. Let us shift gears here a little bit. So we cruise right along through. Talking about the STL vector. So STL is, the STL as a thing is very much a C++ concept, but the stuff that's inside of the STL is cross-programming language. STL, remember, stands for Standard Template Library, and we're going to get our introduction to it via this thing called a vector. And a vector holds a sequence of elements like a 1D array, but its size is flexible. It can grow and shrink. Our arrays were static and fixed, but the STL vector can grow and shrink as needed. Because of that, we don't have to specify the size of it when we define it. The space is automatically added as needed. Well, that's handy. Apparently, there's more about the STL in Chapter 17. We'll just be kind of consuming it piece by piece as we need it as we go through the chapters. In order to use the vector from the STL, we have to include it. So include vector. So how do we use it? It can hold values of any data type specified when the vector is defined. So here we have a vector of type int called scores, a vector of type double called volumes. And the most important thing I want you to remember about vectors is they're very, very similar to arrays. It's a list of data, but they can grow and they can shrink. We can specify an initial size if we wanted to, but we don't have to. And we can use square brackets to access individual elements, again, just like arrays. Here we're defining a vector of type int called scores. Notice the angle brackets. That's a bit of new syntax for us. In your angle bracket, less than and greater than now, we're having to specify a data type. Here's a vector of type int with 30 elements. Here's a vector of type int with 20 elements, and they're all initialized to 0. So this is just a little shorthand notation for initializing every element in your vector to the number 0. Here you can define an int vector initialized to some size and contents of vector finals. So it's kind of like copying it, but you're just defining it here. In C++ 11, you can use initialization lists to define your vectors. So just like, again, arrays. Notice though that there is no equal sign between the vector name and the initialization list. So you're just saying vector, int, scores, here it is. There's no equal sign. You can still use your range-based for loop to access the elements of a vector, just like with arrays. Somebody gave me $1 every time I said that this lecture. Very, very similar ideas here. Here's the new piece though, growing a vector's size. So how do we add an element to a vector? So use this strange sounding method called pushback. Pushback member function to add an element to a full vector or to a vector that had no defined size. So if you wanted to add the score of 75 to the scores vector, you say scores dot push underscore back and then pass whatever you want to insert as the parameter. If you want to get the size of your vector, you can do that. You can say your vector name scores dot size open close paren. That'll get me the size of my vector. You can remove vector elements by saying pop back. So use the pop back function to remove the last element from the vector. Pop back remove the last element but does not return it. That's important. You couldn't say scores.popback. You couldn't say something like int score equals scores.popback because what I just said. It removes it but does not return it. To remove all the elements, use clear. Clears out your vector. To determine if it's empty or not, you could say scores.empty. That'll return true or false, yes or no, if it's empty or not. Let's do at least one hands-on of vector stuff here. That one's using parallel vectors. Yeah, let's do this guy. 825. Okay, like I said from the slides here, we have to include vector. Very good. All right, let's define our first vector. So keyword vector, open angle bracket, int, closing angle bracket. Vector name is numbers, initialized with a size of 5. Pretty basic, so we're going to use a for each loop or a range-based for loop. So we're going to say for int, a reference to variable called val in numbers. So for each val in numbers, let's see out, enter a value, space, and then cn to val. And yes, I know it's numbers. Cool. Then we can display it. For int val in numbers, cout val. This is 825. Let's activate. Enter a value. Oh, what are they doing? So, yeah, okay. 10, 20. And here they are. So very good. Simple range-based for loop, or a for each loop, to read and write vectors. Moving right along here to 578. Okay, simple example just demonstrating the size member function. I feel like they could combine a lot of these examples into one, so we're not having to retype everything, but that's okay. Here we have a vector of ints called values. We've got a function prototype called showValues that accepts a vector of ints. Notice how it does not have a name up here. Vector int does not have a name. That name is specified down here in the function header. So we're going to store a series of numbers in the vector. So we're going to say, we're going to loop through it using the old school for loop. We're going to say values.pushback count times 2. So whatever the current value of count is, multiply it by 2 and push it back to the end of the vector, then display it using the showValues function, passing in our vector of ints. And check it out down here, how we're accessing individual elements of the vector using square bracket notation, just like we did with arrays. I said it again. Here's the pushback and pop back. So here we have a vector called values, pushback 1, pushback 2, pushback 3. Here it's going to tell us the size is 3. When we pop back, then we can see the size is going to be 2. We pop back again, then we're going to see that it's 1. If we pop back again, then we're going to see that it's empty. We could call the isEmpty method on it, and we would see that it would return true. Here's an example to show how to clear it out. So if we create a vector of values of size 100, we can see and get the size of it, should say 100. As soon as we call values.clear, that does not return anything, notice. We can say values.size and it will tell us that it is 0. We can check to see if a vector is empty using something like this. when we pass in a vector to this function called average vector, we might want to check to see if it's empty or not. If it is empty, that actually is important because we can't divide by 0. So if our bottom number is 0, that's going to cause a divide by 0 exception. So this is actually good error handling. Again, if the vector we passed into this function is empty, I shouldn't say divide by 0, it's divide by, I don't actually know, it's dividing by an empty vector, and that would not be good. So we're going to check for that case and see out some error message and return AVG, which is going to be 0. A good error checking there. See. Oh, and here's a good summary in the book. The book will do this a lot. If we encounter new concepts like new data types or objects, they'll give us a good little summary of all the cool things that we might want to do with such a thing, like resize. Again, pushback, empty, clear, etc. Almost done. An array of objects. Okay, so we talked about last chapter how to create our own custom objects in C++. It's by far not the last time we'll be seeing concepts like that, but we can create a class called square and do all kinds of square things. And then after we declare our square object, we can say type square is an array, or we have a shapes array that it's a type square of size 10. So an array of 10 square objects. And then we can loop through that array of objects and call member functions on them too. So we can use the array subscript to access a specific object in the array, use the dot operator to access member methods of that object. So we can say, here's our shapes array, get me my shape at location I, and call getSide on it. Yes, there is a header on 584. Just more for a reference, if you want to grab this, it may be used in some other listings in this chapter. So initializing an array of objects, you can use the default constructor to perform the same initialization. You can use an initialization list to supply specific initial values for each object. That's what it's doing there. The default constructor is used for the remaining objects if it's too short. If an object is initialized with a constructor that takes more than one argument, the initialization list must include a call to the constructor for that object. I think this syntax is horrible, by the way. I've never really seen it used in the wild, so take it with a grain of salt. But this would create an array of size 3 called spaces of rectangles, and each rectangle in that array is basically created using a rectangle constructor that accepts 2 parameters and does whatever it does. You can have an array of structs. Here we have a student struct, and it's got a lot of student stuff in it. You can say, here we have an array called class that is of type student, that is of size C size. Yeah, and this is what I was saying earlier. An array of structures can be used as an alternative to parallel arrays. And I would argue a better alternative, because you're sort of collecting all the data for an individual student together at once. And you can do struct-related stuff, just as you would expect. And let's check out 593. Let me back up. Yes, this is an interesting example that I'm not going to type us through, but you guys should check out. It is my mouse here. There. It's a program that it says test a function that compares the contents of 2 arrays, but what it is Yeah, it's for an ATM machine or an ATM. Wow, a national commerce bank has hired us as a contractor. What an assignment. Your first assignment is to write a function that will be used by the bank's automated teller machine to validate a customer's personal identification number. It must incorporate into a larger program that asks the customer to input his or her PIN on the ATM's keyboard. PINs are 4-digit numbers. The program stores each digit in an element of an int array. So we're going to have an array that stores the PIN for a user. It's not like it's going to be stored in one 4-digit long integer. Each separate digit is a separate element of an array. The PINs are also stored in the database as 4-element arrays. If these two numbers match, then the customer's identity is validated. Functions should compare the two arrays and determine whether they contain the same numbers. So we're creating an ATM, basically, that validates a user and his or her PIN. Check it out. It's kind of a cool little real-world example. Obviously, ATMs are much more complex than just comparing whether a PIN equals something else, but it's kind of cool nonetheless. And if you want to check out the tying it all together, it looks like we're doing rock, paper, scissors at the very end of the chapter on page 596. Again, check it out, especially you game programmers. You may find this interesting as it is kind of a simple game. Utilizing a main game loop in our do while, as well as a variety of data structures. And I should mention that when we talk about arrays and vectors, and structs, I guess, for that matter, generally speaking, these things are called data structures. They're structures to hold data. And virtually all programming languages have a set of data structures, like the array, like the vector, like the struct. They may call them different things, like C# has a list, is kind of what I would call C++'s vector. Most call them arrays, but there's also a lot of other ones, like a queue, there's the stack, there's my personal favorite, a graph data structure, which is not like a bar graph or a line graph. This is a computer science notion of graph. And there's all different kinds. And one of the great things about the STL is it kind of has all that stuff programmed for us already. We don't need to program how a vector works, like under the hood. We don't have to care how it resizes if we're adding things to it or removing things from it. We don't have to care about like what isEmpty does under the hood. The STL handles all that for us. It keeps us blissfully ignorant as far as how it all works under the hood, as any good library should. And again, C++ calls this collection of data structures the STL. Other languages may call them other things, but any decent language is going to have some stuff like this for us for use in our programs. And this is like extra tools in our tool belt, I guess. Sometimes we may need a vector, sometimes we may need an array. If you need fast, use an array. I would say fast but inflexible, use an array. If you need slower but much more flexible, use a vector. Okay, I think we may have made a record time here, which again, I hope is a good thing. If it's not a good thing, let me know. I can definitely slow things down and go through more examples, kind of line by line, hand typing them. As we maybe hand type them together, you can pause the video and slow down or speed it up as you need. But definitely open to feedback. If you like the slower mode or the faster mode like we did today, let me know. And we will see you here next time for Chapter 9.